Hello there, I am Ferdinando Villa from the Basque Centre of Climate Change. My team and I have spent the last few years building ARIES, which stands for Artificial Intelligence for Ecosystem Services. ARIES was originally funded by the US National Science Foundation, and it's the incarnation of a vision where data and sophisticated models can be served to policymakers in a more practical and in a more efficient way. ARIES is not a model, but a platform where models are built, calibrated and run on demand by assembling the data and algorithms that best fit the spatial and temporal context of interest. Data and models live and run on the web, automatically linked by artificial intelligence algorithms that use semantics, machine learning, and machine reasoning to guarantee the best results. In this presentation, I will introduce ARIES from a non-technical point of view. I will show an early preview of the ARIES web interface, which we call the Explorer. We also produce tools to develop new models and network software to contribute new data models to the ARIES platform. Let's begin. What we are looking at is basically a web page with a standard map that you can change in the background. The system at the moment is not distributed as a web application, meaning you cannot go to a website and use it because it would be very expensive for us to provide the service. What you can do at the moment is to download a piece of software that, once installed, enables your machine to work as the web server, basically, and all the calculations are done on your machine. We may eventually make the system available as a web application as well, depending on funding agreement, etc. So whenever you want to know anything about this environment, which you have set as your context by moving around in the map, you can ask your question by typing, and the input bar will respond to your typing by showing you the matching concepts that are known to the knowledge base that is shared around all machine and all users for the string that you typed. So we can choose elevation, which is an easy query, and just press return once again to observe the concept. Once the observation is finished, in this case it's very, very quick, you can click on this checkbox and admire your elevation data, which have been computed at a default resolution that has been chosen for you of 1 kilometer, more or less. If you reset the context and look at here, the resolution changes as you move around, but you can, of course, set your own resolution. For example, we may want to say 300 meters here. You have several choices, and just ask for the same thing again, and you will get a map with much better resolution. So here we are. It will take a little longer to show it. And yeah, the resolution, if you zoom in, you will see that there are many more pixels in there. You can get more details about this map and look around in better ways. You see now that it's like 1,200,000 pixels for this elevation data. We can, for example, observe something that is actually only observable through a model, like, for example, a normalization of elevation. Normalize the elevation. You see the system guides me through the building of this query. And if I ask for this, the system knows that it needs elevation, but then it needs to normalize it. And this is automatically built by the system. As you see now that the values are 0 to 1, as you can expect, etc. If you ask for something that is not data, but, well, maybe not numbers, but object data, vectorial information, for example, cities, I can go somewhere a little closer so we don't get too many. I can ask for a city, and there will be always an explanation coming from the knowledge base. The system will look for all the cities in this area. Here we are, so we have cities here, and we can see them as points in the map, and you can actually list them. Again, we can ask for observations that require some further processing, like, for example, distance to city, which will be very quick as well. So we have a distance to city. This will be a quality, so it will be data. and it will be basically computing distance to the city in meters based on the cities themselves. So you get the drift here. So basically the system is an intelligent modeler that can react to words expressed in a particular semantics, which we develop very actively. And by basically building a model based on network resources and finding the resources that are the best in terms of fitting your context, both in terms of the resolutions that you have chosen, the temporal context that you are in, and the particular context of your observation, desired observation. Now, obviously, nobody is here to build coverages of cities or elevations, so the most interesting part of the system obviously comes when more complex models are requested. And of course, you can always build your query by hand, but it's very useful for particularly if you have a particular area of interest to have a place to start from. And at the moment, before the final release that will produce more palettes and better toolkits in order to orient yourself through the system, now we have this space bar. Basically, if I press the space bar, the system knows who I am because users of the system have a set of groups associated with them. And if you are in the ARIES group, you are supposed to be interested in ecosystem services. So you will get all these choices that have to do with ecosystem services. So for example, I may be interested in the carbon storage in the vegetation. I can choose from there, and the system will find the best possible model for this area that computes the carbon vegetation storage for me. So what I can do is to look at the model as the system is running it. And as you can see here, this diagram, which has been built by the system, basically describes the computation that the system has chosen for this particular problem. The diagram is interactive, so you can click on each piece and get to know about the specific computation that was done in that particular piece. So for example, everything that is green is usually data, and in this case they come from web services, so I can click on the data set, which in this case will be the land cover type, and I can read everything about this data set in this particular and how it's been used and where it comes from, the URLs, etc., etc. And we can close this as well, or we can we may want to know how the original data were classified, so you can look at all the classifications that in this case is the classification of the land cover type, but it can also classify into regions, etc., etc. There is every sort of computation is documented with full transparency. And as you can see here, this is basically implementing the IPCC method for vegetation carbon storage, which is a gigantic lookup table. So it gets these 5 inputs, and you can click on that and actually look at the lookup table itself, which is 1,000 and more lines. And you can explore it and export it, and wherever you feel like doing, it can be done. At the same time, you have your data here, and obviously we haven't looked at the data yet, so we may want to do that. So we have carbon values around here, etc., in tons per hectare, and the system puts all the other information, the remaining information that it was used to compute it, behind it, so to not confuse the view. And at the same time, in addition to building a model and running it, the system also writes a report, or a paper if you want, where everything is cross-referenced. You have references, you have discussion methods, etc., etc. This particular method is quite simple, so there isn't much to say about it. But there are much more complicated models for this entire system. So for example, we could look at the value of outdoor recreation, and we are basically using here implementation of the Estimap model for that, with several variations in order to make it possible to run globally, not just in Europe. So if I click on this, the system will take quite a bit longer to compute this one, but it's already working on that. And as you can see here, the model that has been built, we still have the data flow for the previous one, but the model that has been built is quite a bit more complicated. It takes water body presence, distance from cities, the conductance for the travel, connections, etc., etc. Computes a theoretical recreation supply, then demand for recreation, and then you will put them all together using a Cobb-Douglas function, which you can look at over here. Here we are. So you can document every step. You have the equations that are being computed, and every piece of data documented. Every lookup table is appropriately documented, etc. So we can wait until this is computed. Typically, this kind of models at this kind of scale take between 30 seconds and a couple of minutes to run. And the system is capable of running fairly complicated analysis like hydrological analysis, etc., etc. So as you can see here, several data have been computed already. For example, this will be the demand for outdoor recreation. That is, in this case, is coming from cities. And you can see that there is a big concentration around cities. So we now have along with the carbon vegetation mass that we were computing before, we have the value of the outdoor recreation, which is computed with a Cobb-Douglas function. So now we can admire this map. The value in this case is 0 to 1. Is basically an indicator, not just not a real monetary value or anything like that. For the system, anything that is computable is just a model. So economic values are completely possible to compute as well. We just don't have the models for them at the moment, but we are starting to build some of them for the simplest monetary valuations like timber and forest goods, etc., etc. Now that we have finished the second observation of a much more complex ecosystem service, if we look at the report still keeps the carbon models description, so it keeps all the information from before, but it also contains the outdoor recreation chapter, basically, the section, and as you can see, it includes lookup tables used, etc., etc., and it will show, along with the results for the previous computation, also the results for the next ones. And the references, as you can see, are quite a few more than we had before. Now we could just print this report and be happy with that. We can also keep this around and keep going back to this, or even save this computation. The reason why we may want to eventually repeat the same computation is that the system will always try to find the best possible model for the situations you are in, and that model may change according to the availability of new data, new model components, etc. Models are not just monolithic models. They have no fixed structure. Basically, they are built by putting together components that are built and assembled on demand whenever you ask for an observation. But before in science, it's very important to be able to repeat the same computation for checking, calibrating, etc., etc. It's also very important to be able to save a computation and do that. As I'm showing here, we're still looking at the model and we're looking at all the equations that are part of the model in here. Now, one thing that might be very important is that, of course, as you can see, as a user, I do almost nothing when I try to make an observation, but in very many situations, it's important to be able to parameterize our observation. So, for example, if I was looking at values of outdoor recreation, but instead of using the typical assumption of 20 kilometers around cities as the minimal trip that people will want to make, I want to choose another one because I want to try another scenario, or any other kind of parameterization that I would like to change. The system has an interactive mode that I have to engage explicitly so that the experience for a completely basic user is not made complex by too many questions. But if I engage the interactive mode and then I run something again, like for example going back to that value of outdoor recreation model, as soon as the model has been built, the parameters that the user can change and the modeler can decide which ones can be changed are exposed, and the user is given a chance to change them before the run is executed. There are some very complex models in here that basically take the entire set of services that we have built and perform a multiple criteria analysis so that they can give you a subjective view of the environment based on the concordance between specific priorities that your decision makers may have and all the values, let's say the objective values that the system produces. So if we, in interactive mode, compute one of those models, this is a giant model, so I'm not going to compute it entirely because it will take maybe 5 minutes. But I wanted just to show you that in some cases, in these cases, for example, you can personalize the weights for all the different ecosystem service values. So, for example, for a particular decision maker that I'm impersonating, pollination could be more important because I'm really interested in agriculture, so I can give it a 5. And I could give 1 to sediment retention and maybe 3 to carbon storage, etc., etc. And you have more parameters depending on what models are brought into this particular data flow. The system will show you many parameters. Now I'm starting to compute it so that I can show you the data flow for this one. As you can see, it's quite complicated. And again, you can follow the model, as you can see, as it computes. There is a black one of these things, the one that is computing at the moment is black, and you will see the computation moving around as the system progresses, and the elephant will be spinning to show you that the computation is being computed. Now I will interrupt the task before anything is done, so I don't have to wait too much. Now I don't want to be too long because it's been going on several minutes already. I will just conclude this very, very quick tour of what we are providing at the moment with a mention of the fact that it is possible to use in a very intuitive way data that the users have, and oops, I'm still in interactive mode, submit. And the way to do that will be to just drag and drop a dataset over the semantics that the dataset provides, because one of the difficult things in the system is the semantic annotation of information, but you can use an existing model as a template. So you can take a data file and you drop it over here. The data will remain on your machine, but from that point onwards, the system will be able to use your own data for that, and then it will be your choice if you want to make them available to others or not. And the system will have the complete ability of running scenarios, and actually when models submit scenarios and actually intersect scenarios that have been saved in advance, like for example IPCC scenarios, those will appear in a window that we still don't have at the moment. And it will be possible to click on them and to recompute something under different scenarios, and then compute and check and compare the different runs. So with the background of the flood regulation values of the watersheds of the Pyrenees, let me conclude this extremely quick tour by mentioning that we never intended ARIES to be the platform for our own models. We obviously will are making a big efforts in providing models, and not only that, but also building more that will be available for the future releases, so to cover the entire area of interest for ecosystem services. But because models are built of components that are not necessarily developed by the same people, actually a lot of democracy is allowed in the principle that is behind ARIES. So the idea is that whoever is an expert in a particular topic can write the perfect model for that topic, and that model can be seamlessly integrated with all the other models. So what we want ARIES to be is a democratic platform where the best models are always used to obtain the best results without the complexity that comes from actually having to learn and understand and link all these models manually. So with this, I'd like to conclude it. And one big area of interest for us is the ability of incarnating and becoming a reference implementation for standards. like IPCC standards or SIA standards or whatever standards, as long as they are computable from data and with equations or machine learning or a hydrological model or whatever other kind of model that ARIES can incorporate, it is something that we can put into ARIES, and as you can see, we can put it at the fingertips of decision makers very quickly and very simply because of the facility of using the models through the web. So with this I conclude, and I thank you for your attention, and yes, I'll see you around at the next occasion. Thank you so much.